people. There it is. Look at it. Lovely. Fundamentals, theorems, zero theorems. All right, so we're having the discussion about the zero theorem, and that meant I can write it in a factored form because that's what's easiest for me to graph. Right? Zero product property once I know my factors. It's hot here. So a little review from yesterday. We know we have, remember this relationship between factors and their zeros. If I have a zero, that means I can write a factor. If I have a factor, I can write a zero. That's what we were working on yesterday. So if 3 is a zero of this polynomial, then we're supposed to write it as a product of first degree. What does this mean? First degree factors. Give me an example of a first degree polynomial. First of all, first degree polynomials create what? A line. Very good, Austin. They are lines. These are lines. So when it says a first degree polynomial, that means, give me an equation of a line. Anything. F of x equals x? Sure, that one would work. Y equal x would work. Anything that's in slope-intercept form, basically. Y equal mx plus b. So that's all that this means. First degree factors just mean I want to break this thing up so that I get binomials. X plus a number, x minus a number. That's what we want to end up with. So if 3 happens to be a 0, well, let's put synthetic division to work. You guys are going to be so good at synthetic division. 1, 3, and 2 is 5. 8 minus 11 is negative. Wait a second. Did I miss something? Did I screw something up? What did I do? 3 and 2 is 5. Oh, 15. Hey. 15. 15 minus 11 is 4. There we go. And then I get a 0. Remember, this is what I want to see if I want to find a 0. So 3 is a 0, which means now x minus 3 is one of my factors. And then this. X squared plus 5x plus 4. Can we factor that? Yeah, can. X plus 1, x plus 4. So what I've done is I've used synthetic division to break my polynomial down all the way into factored form. So now I can write it as linear, linear, linear. Those are all linear factors. They're all mx plus b stuff. So I'd say p of x then is equal to x minus 3, x plus 1, x plus 4. So that's my zero theorem at work right there. Being able to break things down into factors. All right, but we were doing a little bit of this yesterday, so that's nothing new. Let's roll. We're probably I don't know if we might do some graphing with this just to remind ourselves of things regarding our double zeros. Like double zero, we talked about that yesterday. Does anyone remember what double zero meant? Two of the same zero, right? Yeah, two of the same. And graphically, what does it mean? A bounce. It means I bounce. So remember, the double zeros mean you bounce. We bounce off of my x-axis. Whatever that x-intercept is. So in this case, -1 is my 0. So as a factor, it's x plus 1. And because it's a double zero, I know that this means actually x plus 1 squared. What that is. All right, so we're going to do breaking this thing down. Again, notice the 4th degree. We're going to have a double zero. So what does this allow you to do? Well, it allows you to do synthetic division twice. So we set it up. And again, I'm doing the shortcut method. So if negative 1 is a double zero, that means I should be able to do synthetic division twice with negative 1. Now, does it make sense to do it twice with the same setup? No, because I know I'm going to get zeros. So this is the nice thing about synthetic division. Once I find one of the zeros, then I restart the process with the new polynomial, the new quotient. So what does that look like? So negative 1 we're going to test. Hopefully you get a 0 over there. Negative 1 minus 3, negative 4. 4 minus 3 is 1. Negative 1 and 7 is 6. Negative 6 and 6 is a 0. So that, as it should have been, produces a remainder of 0, and that is a factor x plus 1. So here's what I would do at this point. Remember, it started as a 4th degree. Now this. So I'm going to put an underline just under those terms. I'm ignoring these guys up here now. I don't need to look at them anymore. And I'm doing synthetic division as if this is my new setup. And we continue the process. So I know that double zero is a negative 1, so when I do this again, I should get another 0 here. So we drop the 1. 1 minus, or negative 1 minus 4, negative 5. 5 plus 1, 6. Negative 6 plus 6, 0. Again, I'm using these numbers here. I'm not using the ones above anymore because I've already found the first 0, and I created a new synthetic division problem, and now I've found the second 0. How many should I potentially have? 4. It's a 4th degree polynomial. I could have 4 real zeros. They might not all be real. All right, so now we found another 0 there. So that's where the x plus 1 squared thing's coming from, factor y. And I could synthetic division the 1, the negative 5, and the 6. But this right now, remember, always breaks down by a power of 1. So now this is an x squared minus 5x plus 6. So here is kind of the goal, at least in my opinion, of synthetic division when you're factoring. Get yourself down to a quadratic. At that point, you can then quadratic formula the problem to find the other x's, or you can factor the problem to find the other x's. And are we able to factor this one? Yes. Yeah? Because I have a positive 6 and a negative 5. So if this thing did equal 0, I'd have x minus 2, x minus 3. And now, I don't need to go find the zeros. I know that the zeros, which would help me graph, the zeros would be 2 and 3 here. But what were we initially trying to do? We're writing it as a product of first degree factors, meaning we're factoring this thing. That's all we're trying to do, is make it look like a factored form versus an expanded form. So far, we know from what I have found in my zeros, x plus 1 would have been a factor for that term. It would have shown up again for this one, x plus 1. And then here are the other two that we just found, x minus 2 and x minus 3. So if I put all 4 of those together, I will have the factored form for this polynomial. And that's kind of what we're shooting for. Yes? Yeah, we do. We want to, if I have it, that's again a repeated value, I'll use the power of it. Yep. So finally we get to this. P of x is equal to x plus 1 twice, multiplicity of 2, x minus 2, x minus 3. And now what this does, here, let's just kind of go and do a little preview. What does this allow me to do, graphing-wise? Check it out. Watch this. It's a nice. Once you're in factored form, it's beautiful. Because I have x-intercepts. I have zeros, which are my x-intercepts. And they occur at negative 1, 2, and 3. So we go put our points in, negative 1, 2, 3. They're my x-intercepts. Now, because we understand behavior of polynomials, I can sketch this without having to find exact values. I will be looking for shape. not exact values. What do I mean by shape? The degree is a 4, which means it's even. The leading coefficient is A. Well, if you look up here, if I were to go back to the expanded form of this thing, what's my leading coefficient? It's a positive 1. It's right there. It's a positive 1. So my leading coefficient is positive. So hopefully what you know is that for even functions that have positive leading coefficients, they start up and they end up. It's going to be a W looking thing, exactly. Yep. So similar to the left-hand side of this negative 1, 0, which is the furthest left intercept, I'm going to have my graph coming down. It's going to be coming down, and somewhere's going to make a turn, and whoop, it's going to make a turn again. Whoop, there it is. Whoa. Whoops, I lost my bounce. Let's try that again. I'm supposed to bounce off of the negative 1. So we come down, and I boing, bounce, and I'm going to switch, go through, switch, go through, and that would be my curve, something that looks like that. Now the wider, the further apart your x-intercepts are, that means this little bump, whether it's like the crest or the valley, the wider your x-intercepts are, in theory, your crest or valley is going to be higher or lower. And so really, maybe this doesn't go down quite so low. Maybe it just does a quick change, something like that. These guys are called, like that thing right there. It's called a local maximum. And then hanging out down here would be called the local minimum. They're local because they're not the, well, in that case, that is the minimum. That is the actual local point. But this isn't the highest, the local maximum isn't the highest point. It's just the maximum of that little area within my x-intercepts. That's why we call it a local maximum. The graph keeps going forever in the y direction, so it actually doesn't have a maximum. But in terms of what we're looking at, that would be the highest point right there. So, preview of things to come, free of charge. I'm not going to charge you for that information. You're welcome. All right, so this is what we're going to be trying to do now. Given some zeros, use synthetic division, find the factors, put all the factors together, and then hopefully be able to graph this. You guys want to try that one? Or you can try that one. Or you can try that one. How about we try that one? Let's do that. Did I go too fast? How's that look? You guys get the same things? So we were unable to factor that quadratic. But are we still able to write a factored form of first degree polynomials? Two of our values, two of our zeros are imaginary. And that's okay. You can be imaginary, that's all right. So two of them are real, two of them are imaginary. So here's what I should have. I have p of x would equal x minus 3 squared. There's our two real ones. And then the two imaginaries, remember we did this yesterday. Always go x minus. And then we're subtracting a 3 plus an I, but we're also subtracting a 3 minus an I. These guys are called conjugates, remember. And then we could go and simplify over there. X minus 3 minus an I, and an x minus a 3 plus an I. And as we did yesterday, we talked about how these x minus 3s are like the real parts of that complex number. And then vi, or 1, or negative 1i in this case for the second one, would be your imaginary parts. So that would have been my polynomial here for that particular problem. You guys get something similar to that? Rice, did you get that? Who goes to Rice?
No.
Oh, you just want to go there?
No, my uncle was.
Oh, very cool.
Will that be graph?
Will that be what?
Graph.
Okay, good question. Could we graph this thing? And the answer is yes. We obviously won't be graphing the 3 plus I and 3 minus I.
It just bounce off of
So it just bounces off of a negative 3. So it's a fourth degree, right?
Yeah.
So what would this look like if it just bounced off of a negative 3? Well, that's a good question. Yeah, it's going to look like a parabola, exactly. So it's going to bounce off a positive 3. And it's going to come down. It's going to kind of flatten out and then go back up. Kind of looks like a parabola, just gets a little flatter down there near the x-intercept. Summer.
I'm kind of confused. Why did you put, like, I know you put an x there, but why did you put x minus 3 minus 5 and
Why did I do that?
yeah.
So when you did the quadratic formula and you got x equal 3 plus or minus I, I'm trying to write this thing in linear form.
Oh,
So I can't write it as x squared minus x, 6x plus 10. I have to break that down into linear components.
okay, and it would be x minus because it's positive.
Well, first of all, when I'm setting up factors, they're always going to be x minus whatever your r value is, every single time. Sometimes, though, that becomes a plus because maybe your r was a negative 3. But in this case, my r's over here, those are both 3 plus, so it's a positive 3 plus an I, and it's a positive 3 minus an I. So I don't have, that has, these both have to start out as negative every time. Did I answer your question?
Yeah.
All right, moving along, unless there are any other ones. So that's the goal. We're going to kind of skip some of these other slides because it's the same type of a deal. Fractional values of zeros, you can still break things down. Let's try this one here. I have a negative 2/3 that happens to be a 0 because what I want you to learn how to do is when you have a fraction of 0, I want you to write it a little differently than just x plus or minus a fraction. So let's try this one here real quick. 3, negative 10, 31, 26. We're going to test a negative 2/3. I know, you guys love them. Fractions. Okay, so what's negative 2/3 times 3? Quick! Negative 2. Very good. It is negative 2. Negative 2 minus 10, negative 12. Okay, ready? Looking for the fastest one. Negative 2/3 times negative 12. It's okay if you have to do it like this. 8. That becomes 8. And then 8 and 31 becomes 39. Oh, ready? Ready? Here we go. Negative 2/3 times 39? Huh? Negative 26. It's going to be negative 26, which makes this become 0. All right. Yeah, you could have cheated on that. You know it's supposed to be a 0, so I could have just written 0. All right. Okay, so then I've got a 3x squared minus a 12x plus a 39. What would you guys do in a problem that looked like that?
Looking at that book.
I would go watch TV. Yeah, I pull out a GCF. So I pull out a GCF. Thank you, Austin, for your support. Okay, and then what are we going to have to do on that one again? Yeah, this one doesn't factor, does it? Factors of 13 doesn't give me a 4. So I have to do quadratic formula on this one once again and end up with some, let's see if we're going to get some, remember, what's the quick way? You guys remember the quick way to determine whether or not you're going to have imaginaries? Discriminant. Very good. So remember that this is a very quick way of determining if I get real roots or not. If this thing is less than 0, there's no real root. If it equals 0, there's one real root. And if it's greater than 0, there are 2 real roots. So very quickly we can tell. So b, negative 4 squared, 16. 16 minus 4 times 13. 4 times 13 is 52. So 16 minus 52 is a negative number. No reals here. These are going to be imaginaries. So I'm going to have some negative b plus or minus 16 minus 4 times 13 all over 2 times 1. 4 plus or minus the square root of 16 minus 52 is 36. Negative 36. 4 plus or minus 6i over 2. Factor 2 out of the top. Cancel those 2's, and there are your roots, your other roots. X minus 2 plus 3i, x minus 2 minus 3i. And that would be my factored formula. Anyway, I just wanted to do one of them that had a 0 that happened to be fractional, because you can still calculate this thing. All right. Okay, good. Let's take a little stress break. Start this